All right. Hello, everyone. It's a tremendous pleasure to be here again. I think I joined one of the first BEAM session symposia a while ago as a young researcher. I think it was maybe 18 or 19 or so. And it's a pleasure to see how this grows and like how it repeats and iterates. And I've been following along this symposium, and it's a really great institution already. Thanks for having me. As a first speaker, I have the chance to also give a little bit of a background on the research that we do, the context that we do. We probably hear it again, but like most of you know, the world population is rapidly growing. Until 2050, we will reach a peak of 10 billion people, and hence there's a drastic demand for construction that we have to cover, that we have to address. But there's also, of course, a dramatic downside to it, which in regards especially to the consumption of resources. These are the numbers for construction alone. 50% of all extracted material is consumed by construction. This includes 12% of all CO2 emissions worldwide as gray energy. But if we look into operation, this adds up to 39%. And 55% of all waste that is created on Earth is actually coming from construction. If we look at the innovation that has been happening in the last centuries and decades, you can see that there was development on materials and building machines, but fundamentally the processes have remained the same. On the left side, you see the first system formwork that was patented in 1912, where reinforcement is conventionally bent by a person. It's installed on site. Then there's a system formwork that covers the reinforcement, and then concrete is poured into the formwork. And on the right side, you see basically fundamentally the same principle, which is Perry's best-selling formwork system in 2018. And this does have, of course, dramatic implementations on the productivity of construction. Here are some numbers. The red line is the baseline, basically, of construction, which remained steadily low from the 1970s on. This is where the measurement started until today, whereas other industries have dramatically increased their productivity per capita by approximately 300%. And this does not only have economic implications, but also, of course, ecological ones. Since work is expensive and material is being cheap so far in the last decades, constructions like this, which are extremely material efficient, are just not economically feasible to be built, which is a pity. And hence, digital processes, and this is an example from ETH Zurich, they promise that form comes again at no extra cost. So we can print regardless of geometric complexity, and therefore can in the future, hopefully, and this is what we're working on, again, produce material efficient instead of mass intensive. So in this context, I would like to present a couple of research projects from the Institute of Structural Design, which I'm heading together with Professor Harald Kloft, my colleague, since approximately 5 or 6 years. So we're having two large-scale research infrastructures. On the left side, the Digital Building Fabrication Laboratory. It's 12 by 8 by 4 meter build space with 2 gantries, 1 robot attached that is basically open to address a manifold of processes. And on the back side, a portal. This is used for subtractive manufacturing. That is an ever becoming more important in our processes. And on the right side, we have a new setup. That's the digital construction site, which has just been inaugurated, and where we want to investigate networked construction processes on site. And I will elaborate on this a little bit later. So in the DBFL, we are looking at, as I mentioned, manifold of processes, from 3D printing of steel to shotcrete 3D printing as technology that we have invented in Braunschweig, to subtractive processes, where we, for example, look into dry joints and connections for disassembly, but also collaborative robotic processes with alternative materials, as for example, earthen materials, as in this rammed earth, robotic rammed earth project. Generally, we could try to cluster our topics a little bit, and we have lately come to a categorization where we say we have a couple of processes that work on material reduction, using less material, using more intelligent forms. We have a stream that we have projects together also with Oliver Tessmann that are addressing reuse, and recycling projects where we look into construction debris, how we can further use this, or use materials that are basically infinitely recyclable. So let me start with the reduce stream, so to say. So as I mentioned, shotcrete printing is one of the processes that we are investigating at TU Braunschweig. It's an old process, also invented 100 years ago, therefore well established in the norms and codes, and ready for implementation. Also in the automated version in robotic shotcrete 3D printing. The idea is that material is not simply deposited as streams, but it's rather jetted, and it has a pretty high throughput of material. We can print against vertical surfaces in a horizontal manner, for example, to include consoles or supports. We have a very good layer bonding between the layers because of the pneumatic pressure that the material is jetted onto the previous layers. Therefore, we can do gradual transitions from vertical to horizontal, which helps in the transmission of forces. And then we have sensors integrated into the process so that we have a higher control on this process. And what you can see in this video is, I don't know if it's visible, there's this red line. This is basically a laser that measures the distance between the nozzle and the printed layer. And if this distance changes due to some unforeseen factors, then the robot speed will be adapted so that after a couple of layers, this is leveled out again. So these are adaptive processes. As an Institute of Structural Design, we're also mainly interested in structural components. We're looking into wall-type elements, columns, spatial structures, and also hybrid fabricated structures as these add-on printed slabs, for example, where the floor slab is cast in a conventional manner, and then ribs are printed on top of it where the forces are dominant. So, of course, reinforcement is one of the major issues still in 3D printing, and we've developed a couple of different techniques to address this. The simplest one is that we are printing the geometry basically in a slightly undulated manner, then place horizontal reinforcement on top in between these layers, and then basically thread vertical reinforcement through those valleys that are created, and then apply a second layer of concrete that structurally embeds the reinforcement and hence produces fully structurally reinforced concrete elements. But since the forces in the structure are not predominantly orthogonal. We've also investigated how we could optimize the reinforcement placement and also automate it. And therefore, we worked together with the Institute of Adaptronics and Mechatronics at TU Braunschweig and developed this so-called dynamic fiber winding machine. And here's a short video of this process. So this is the material jetting process, where we print layer upon layer. Then we have a structural analysis of the forces, which is then automatically translated into a print path. And here, a strand that is winded with a helix around it is placed onto the wall with a kind of a stapling process, where a modified stapling gun is used to pin this material on top of the surface. And then the second layer is applied. And later on, conventional tools for surface finishing are used to soften and smoothen the surface. Meanwhile, we are in a little bit better control of the amount of material that is applied, also through digital quality control. But basically, this is the fully automated process to create a load-bearing concrete structure. So, based on these ideas, or this is maybe something that I say in between. So digital quality control, I just mentioned it, to deal with excess material or material that is at places where there's too little or where some accidents have happened. We developed this streamline. Here you can see kind of the worst failure modes that can happen. We have sometimes the material was clogging and therefore there is material lacking somewhere. We have maybe sagging of the material. And therefore we have created this digital workflow where basically the second portal of the DBFL is picking up a laser scanner, automatically scans the wall directly after printing. And then in Grasshopper, there's a cloud compare between the points as they should be and as they are. And based on the differences, automatically a new path is generated that either adds material or subtracts material directly. So there are a couple of iterations of this idea of textile reinforcement. One seminar that we recently held in teaching together with TU Munich with Katrin Dörfler and Pierluigi D'Acunto, and Mariana Popescu is basically an automation of this computational knitting project. Many of you have probably heard. Mariana Popescu is basically computationally knitting a textile on a computer-controlled knitting machine, and is using this as formwork, and then applies concrete manually to this process, which is again extremely labor-intensive. And hence the idea of this collaboration with 18 students, 6 from Delft, 6 from Munich, and 6 from Braunschweig, was to automate this process and to address this process. So in the first step, students were asked to delve into computational form finding of this textile, to analyze where the forces are, where more material is needed and where less material is needed. Then they went to Delft to computationally knit these textiles on a knitting machine. They were then spanned over bending active reinforcement steel rods. And then in a workshop in Braunschweig, this was installed at the Digital Building Fabrication Laboratory. And there with the shotcrete 3D printing method, material was applied in a very thin manner so that this shell could pre-harden to give a kind of a strength through the geometry. And then in the further process, the reinforcement was added through kind of again, a 3D scanning process where the pins were first detected. Then here, first, the robot would wind a reinforcement around the pins. Then additional material would be applied. Then the surface finishing would be applied. And in the end, the corners were cut to precision. In the end, this bridge turned out a little bit thicker than we initially intended, and hence we iterated on this process, also on this process of creating the shape. And this is a process that we call frame winding. Here, a frame is first created in a manual manner. It's basically a steel frame with pins on it. Then the robot would wind around these pins and then apply concrete in a very thin version. And again, here I brought a video of this process. And there's a specialty in this process to prevent the concrete from flying through. So this is a part, again, of a student workshop where we have actually 14 of these elements that create an oval shape as a pavilion. So this fiber winding process, you probably all have seen before, is very similar to the one that Stuttgart is investigating. And then here is this novelty that there's a thin tape layer in between the two reinforcement strands that is applied so that the concrete would be prevented from flying through. So it creates a closed surface, or let's say a semi-closed surface. This tape is available in different porosities, so to say. And then again, as you have seen in the previous process, the concrete is applied in a very thin layer so that a stiff shell is created. And then again, the subtractive part. So we've also scanned this frame before installing it or after installing it. So we know the precise location, and then the corners are basically cleaned or cut in green state so that the connection is possible to the other elements which would complement this structure. There are some issues, as you can see here, with the material shooting through the tape. This is something that we are currently addressing. So another project that we are investigating is the injection 3D concrete printing. This is basically the attempt to release or deliberate 3D printing from the issue of gravity. And we have kind of three versions of it. One is printing a concrete into a suspension that has similar rheological properties than the concrete itself, so that you can create spatial structures that are not built in layers, but in free trajectories. This can be inverted as well. So we can print suspension in the concrete to create porosity, for example. So we just inserted bubbles of a gel, and which is flowing out later. And also we can print a high strength concrete into a very low strength material or isolating material, so that we have kind of an inner skeleton of things where we can address or specifically address loads and supports. So the parameters, this is a project that we are working with the IBMB together. That's the Institute for Materials at TU Braunschweig. And there are a couple of parameters that need to be carefully adjusted, which I can show in the following slide. So basically, the speed is, of course, one crucial issue. If you are too fast, the stream rips. This is nothing new. This is also the case in conventional 3D concrete printing projects. But this one is interesting. If you're going too slow, the material kind of starts curling up, and it creates these funny curls. Then, of course, we have the problem if the suspension that we are using is not dense enough, the material starts sinking, and only if all these parameters are met, then we are in this window where the delta between the density of the material and the density of the printed suspension is optimal, and where we can create complex nodes and straight lines. So the first experiments, of course, showed that compression structures are working pretty fine with this. Of course, the structures are extremely brittle, and so we did first investigations to print around reinforcement, kind of a pre-installed reinforcement or even a pre-winded reinforcement that is within the suspension, and where we have a special nozzle that encases this reinforcement. And we did some structural tests regarding the embedment of it, and it shows very promising results. But also what is interesting is that we can address structures that are predominantly compression active, dating back to Kuhlmann, who invented the graphic statics. And there are also many research groups working on these principles of graphic statics. They have been applied throughout engineering history, but they are very cumbersome to calculate. You have to draw each vector in space. Or let's say here in a plane. So even in 2 dimensions, this is quite labor intensive. If it goes to 3 dimensions, it's becoming even more complex. But with computational tools, of course, this becomes much more easy. So the idea is that the whole structure is always in equilibrium, and that the forces that are acting in one structure are canceling itself out, and therefore you can create very complex structures, spatially, that act in compression only. This is a project of a student group. They were tasked to design a table that acts in compression only, and that they produce in this method. And this is one of these elements of these table legs. The difficulty, of course, is the path planning in this process, because you have so spatially complex elements and you can never cross a path again, right? Because you would destroy what you've created before. So some effort went into finding an ideal path planning for this printing technology. And here they were succeeding. One of these legs, that's another advantage of this production technology, is that you can very rapidly print. So one of these legs is printed in 2 minutes, which is quite fast, and then it rests in the suspension for usually 24 hours, and after that it can be taken out. So this is then also scaled up in a follow-up research project where my PhD student Inan Chao was designing a bridge, or kind of a model of a bridge, a 4 meter span bridge that acts in compression only. And which is then segmented into segments, because we do not have infinitely large vessels to print in. So we rather have small vessels of about a cubic meter to print in. And then we have the supports here, and in the supports the tensional forces are spread, and then there are special connectors 3D printed that you can see here in orange, and these are printed based on a 3D scan. So first all the segments were printed, or maybe I just show the video to it. This is the final structure in the end. And here we have some sequences from the production process. So basically, the parts are printed separately in the suspension. They're taken out, then they're 3D scanned, assembled virtually with a little gap in between so that the connector parts can be printed. And then the real thing is assembled. So that's the graphic statics part. And Inan's PhD thesis is about bringing the fabrication constraints and the structural constraints into one design model that all structures that are created are at the same time checked for production feasibility. These are the three parts. This is then the vessel, and initially we used sonographic gel, which decomposes, but it has the advantage that you can actually see the process and calibrate the process. But for the real printing, we use a limestone suspension, which is based on limestone powder, a byproduct, which is very cheap and infinitely reusable. So with the disadvantage, of course, that you don't know what's going on inside. Yeah. You can imagine the frustration the next day when you come back and it's all in pieces. But yeah, so this is the excavation process. And then it's simply just cleaning, scanning, and virtual assembling. And then this project continues for another 4 years. This was funded by the Volkswagen Stiftung for 1 year. And now we made a DFG project out of it. And the idea is then the further scaling up of this process and also to test the variations of it. Regarding reuse, I mentioned already that we are looking into predominantly subtractive processes here, but which are now combined into with 3D printing processes. This is a project that was running between ETE and the Digital Design Unit of TU Darmstadt. So the idea here is that we take or scan old structures which are then cut roughly into pieces in the DBFL, for example, and then which are then computationally assembled into new structures. And here on the left side, we have these steel pockets, which are still fairly standard parts. But now, with combining this with one printing, we are working on other more elegant jointing principles for these structures. So then the last kind of cluster that we are looking into is the recycling approach, where of course one of the biggest disadvantages next to the issue of reinforcement is the aggregate size that can be used in 3D concrete printing. Usually there are tendencies towards larger aggregates, but many of the structures that are being printed are printed with mortar rather than concrete and have a maximum aggregate size of 4 millimeters. So here the idea was that we can use construction debris to incorporate it into new 3D printed structures. And we call this large particle 3D bed printing. And it's basically a combination of shotcrete printing together with particle bed printing technologies. So again, this was a collaboration with our materials department IBMB, and the challenge here is to find a sieve curve for the aggregates that allows the concrete to protrude fully, so that there are no voids created in between the layers, so to have a solid structure. And what we used here is 32 and 16 millimeters aggregates, and therefore we can replace a substantial amount of cement that would usually be used with recycled construction debris. And then, of course, the surface is rather rough, right? So, I mean, another advantage is that the material supports this printed structure the entire time. So we could also think of using low cement binders for spraying. But here comes then the secondary process, where the other portal of the DBFL is used to fine cut the surface. So we take off a couple of millimeters in this milling process, which could be done for aesthetic reasons, because you get this really nice 3D terrazzo effect on the structure, but also of course, for joining structures, joining building components. There's a close-up of the surface that is created after milling. And then we have a whole research stream lately that looks into materials that can be reused many times. And we're looking into traditional earth constructions and trying to bring this to the digital age, to make it also more efficient in production, because unfortunately they are extremely labor intensive. And here we are investigating these collaborative processes. This should be a video. Click on it. Sorry, but I think you've seen it before. Yeah. So basically, one of the robots is laying out the earth, and the other one is compacting it. It has a slipping formwork, so that the formwork is only needed at this very moment where it's compressed. And below that and before that, it's compressed anyways. So there's no need for formwork anymore. And then also, of course, spraying concrete, spraying earthen materials. And here it's interesting to us that we can basically use the methodologies and techniques that we've developed for shotcrete and adapt them to other materials. So basically the processes are more or less identical, but the parameters are different. One major advantage of using digital processes. And then, of course, printing with earth. This is something that we are using a lot with our students, because it's also a very pleasant material to work with. There we fabricate things in large scale. And now, lately, we want to go out of the laboratory. And this is also a video that doesn't play, unfortunately. This is there should be our new digital construction site. Maybe we can see it later again. Maybe I can click on something. There was something. Yeah, but it doesn't show. So that's unfortunate. I think you saw a little bit of it before. So the idea is that on the construction side, we of course want to investigate the entire digital chain from design to the operation phase, but concentrate on the production phase on the construction side and have a whole entire network of different actors that work together on the construction side. And these are, this is a collaborative process, a collaboration between these partners here. Markus Gerke from the Institute of Photogrammetry, then Harald Klofte me from Structural Design, Dirk Loke from Materials, and Patrick Schwertner from Building Management at TU Braunschweig. And so we have also these components addressed in the entire setup with 3D tracking systems that would allow us to track material streams and construction workflows. We have a mixed reality setup that would involve humans in the construction process. Then a 3D printer, which is a cobalt printer, but which is modified in a way that it's not installed yet, that will have a robotic arm as well for assembly processes, and a fifth axis. And also a couple of mobile robots that could work on the construction site together with these other actors. And this is fairly new, and we've only inaugurated it and have done some preliminary tests. Here are the mobile robots. Again, this video is not playing on the right side, where we kind of, as a first step, bring these processes onto the construction site and see how the different machines and different actors can work together in basically seamless digital processes. So many of these processes are and materials are part of the AMC. That's a Collaborative Research Center that our institute is heading under the spokesmanship of Harald Kloft at TU Braunschweig, which is a collaboration with TU Munich. And there are three areas, one focusing on materials and processes, one on simulation and modeling, and one of implementing these technologies into the construction process. And these are the PIs and an email website of the TRR, which you are happily invited to learn more about the processes that we're investigating. And with that, I think I'm a little bit ahead of time, more time for questions, but that will be it from my side. Thank you very much.
So thank you very much for your presentation, Norman. Particularly love that approach using shotcrete as binder jetting. That was new to me. I haven't seen that yet. And I'm keen to see more of that sooner or later, maybe next year. Questions from the audience? Just raise your hands. Okay. I come from that side.
Thank you very much for the nice presentation. Do you envision collaborating with industry firms to develop your methods?
Yeah, so we are quite diverse in our collaborations. Some of the things that I've shown were predominantly basic research in the DFG-funded Collaborative Research Center, but also we have a couple of collaborations with industry partners where we trying to bring these technologies that are a little bit more advanced already into industry. So we have collaborations with some material suppliers to also look into other materials that we could shotcrete. Silightment is one of the materials that's a low carbon kind of a cement alternative. With reinforcement manufacturers, with 3D printing startups, and so we would love to see that this more applied, and approach us when you want to collaborate if you are from industry. Yeah.
Thank you.
I have a question about the structural analysis of these structures, particularly the reuse, the last one where you had this debris bound with concrete. Is it possible to have a structural model of it before you do the actual object and kind of analyze the structural stability? Because that is one of the biggest problems with concrete debris. that you're not able to know the structural stability of the object? And if so, how you tackle the situation?
So, yeah, you're right. So we don't really know what's always in there. So you can there are some demolition firms that pre-sort that offer concrete debris. This one, there was also plastic parts in there, like old light switches and stuff. So I guess this wouldn't contribute to the structural stability. So it really depends on what you get as debris, right? So if this is characterized to some degree, that depends on the supplier. But also in this process, we did some preliminary samples, and then took bore cores and did compression tests to see where we are at in terms of strength, and then can use this information given that we have the same material and for the real structure, to design our structures. Mm-hmm.
Thanks for the great presentation. And I think that's following you up from mesh mold to what we have saw today, which is mesmerizing packet of the developments throughout the years. We have saw the conventional way of putting the threads, which are like more related to the construction industry, and also the winding patterns. And from you, I would like to hear where is the potential to delivering it and transfer to the end industry? Where do you see the most potentials? Because it's like the bottleneck of 3D printing in our industry. And I think this insight from you would be very interesting to me.
It has a lot to do with existing codes and regulations, and for conventional, like layer-based 3D printing, I think the current state of the technology is that you cannot assume it as a structural element, and that it's basically calculated as a lost formwork. And with shotcrete, we have the advantage that this is regulated in the norms. So basically, we can work with existing norms and could apply it. Now, what we think could be very interesting is in coastal protection, for example. So where we can really use these geometries that we can create, these complex shapes. And we have a research group on that to apply it to urban coastal protection systems. So that would be a pretty direct, let's say, use case. Then in other collaborations, we're looking into how can we apply this technology to buildings that exceed like 3-4 levels, right? That are where we can make more use of 3D printing technologies, because I mean, it's questionable if we should 3D print single-family houses, right? Or even using this technique, because it will overperform. We could use maybe other materials or lower-performing materials. But these are the two streams that we are looking into, kind of more the infrastructure-related things, especially coastal protection and 6 stories plus housing. Yeah.
Okay, any more questions from the audience I've overseen yet? No? All right, then. Thank you for the presentation, and it was a good insight on how powerful such a Transregio project with multilateral universities contributing to a joint research can be, and I think it's a good motivation for more Transregios in the built environment. So hopefully, looking at you two. I want his setup in Darmstadt, but first we need the facilities, and then we need the setup. And I will be gone because they will kick me out after 5 years. Okay, so thank you very much. One applause for a moment.